Today we're gonna learn how we can use derivatives to understand the behavior of functions. So let's start with considering the function that has a derivative greater than 0, either at some point x or in the range of points. So what's happening here? Well, first of all, let's look at the derivative. The definition of the derivative. It's a limit of the ratio of the change in function to the change in the argument, right? And when this limit is positive, it means that the function itself, like whatever's inside of the limit, is going to be positive for small values of delta x. Okay? So when you look at here delta x is quite small, okay? But still it's finite. We can consider two cases. One case when delta x is positive, the other case when delta x is negative. Now, when somebody writes this limit like this, and they say delta x should go to 0, here what they mean is we should have the same value of the limit regardless whether delta x is positive or delta x is negative. We should get to the same value, because if we don't, if we take delta x as positive, we get one value. If we take delta x as negative, another value, it means that there is no limit and there's no derivative. Let's say we have delta x positive, right? So with delta x positive, whole thing should be positive. It means that numerator has to be positive. That's what's written here. And that means that f of the x plus delta x should be greater than f of x. Let's draw these 2 points. We have x plus delta x. Since delta x is positive, x plus delta x should be greater than x, right? And here the values of the functions, f of x plus delta x is larger than f of x. That's what we said. And that really means that function is increasing. Okay. All right, let's consider another case when delta x is negative. Well, denominator is negative. Numerator also has to be negative, so for whole thing to be positive. It means we have the opposite thing, that f of x plus delta x is less than f of x. But now, if you look at the graph, we find the same behavior. Our function is growing. That's because x plus delta x in this case is less than x. And that's because delta x is negative. Okay? So what all this thing tells us, regardless whether delta x is positive or negative, if the derivative of the function is positive, function is increasing. Now let's look at the opposite case when derivative of a function is negative. Again, we look at the limit, and limit is negative when whatever's inside of the limit is negative for small delta x. Again, we consider 2 cases. One case, delta x is positive. If denominator is positive, whole thing has to be negative. It means that numerator has to be negative. And that means f of x plus delta x is less than f of x. If we draw these points, we find that the function needs to go down if derivative is negative. Well, let's consider the case of delta x when it's negative. In this case, f of x plus delta x should be greater than f of x. And the picture actually looks very similar. So no matter what delta x is, whether it's positive or negative, the function has to decrease if derivative is negative. Okay? So now what we know, if derivative is positive, function goes up. If derivative is negative, function goes down. Now, next question is, what happens if derivative is 0? Is it going up, going down, don't go anywhere? Well, for one thing we know, we discussed it before, if derivative of a function is 0 everywhere for every x, we said the function doesn't go anywhere. It has to be constant. But what if the derivative of a function is 0 at one point? what's happening in this case? Let's consider the following function. F of x equals 2x cubed. I will take derivative of this function. It's going to be 3x squared. And we can see that derivative equals to 0 when x equals to 0. In fact, the function looks like this. So what happened with this function? At 0, where derivative is 0, the function actually doesn't stop increasing. It keeps going and going and going. And the reason why derivative is here is 0 is because if you remember what derivative is, and it's a slope of tangential line to this curve. And when derivative is 0, it simply means that tangential line is horizontal. There's a slope of 0. And in this function, if you look to the left of x equals to 0, derivative is positive, the function is increasing. For positive x function, derivative of the function is also positive. So the function keep increasing. Okay. Now let's look in the opposite case when the function is minus x cubed. Again, we take derivative. It's going to be minus 3x squared. And derivative equals to 0 also at when x equals to 0. The function is continuously decreasing function in this case. And again, at point 0, we have horizontal slope of a tangent line. That's why derivative is 0. But for negative axis, derivative is negative, so the function is decreasing. For positive axis, the derivative of the function is less than 0 and the function is decreasing. So really, even going through the point 0, here and here, the function here is increasing through 0 and here is decreasing through 0. Okay. Now, let's look at the function that changes the direction. It's increasing, then it's decreasing. At this point, it reaches maximum. So first, let's look at the left side of this curve. Notice the function is increasing everywhere, and it means that derivative here should be greater or equal than 0. Okay. Now, if you look at this function on the other side, the derivative should be less or equal than 0 because the function is continuously decreasing. Okay. So, but now the question is what to do at this point. On one hand, if you look at on the left and we calculate derivative at this point purely on the left, okay, for delta x negatives, the function is increasing. So the derivative should be greater or equal than 0. If you look on the left, we find that derivative of the function should be less or equal than 0, even at this point. Okay. But when we talk about this point, again, we need to take a one-sided limit for delta x greater than 0. But now we actually need to reconcile. On one hand, derivative here should be greater or equal than 0. On the other hand, it should be less or equal than 0. So it means the only way to match those cases is to have derivative at that point to be 0. Okay? And it makes sense because at that point the slope of a tangent line is horizontal. Kind of makes sense. So before slope was positive, the function was increasing. Now we got to the 0 slope, and then the slope become negative and the function is decreasing. Now let's look at the opposite case when the function reaches minimum. Now on the left the function goes down, so derivative should be less or equal to 0. On the right, the function is increasing, derivative should be greater or equal than 0. And obviously to match or reconcile the values of derivative for this particular point of minimum, you have to assume that the derivative at that point equals to 0. Right? And the slope again is flat here. It's horizontal for the tangent line. And that brings us to actual theorem that tells you that if I have a point x equals to x naught, which is maximum or minimum of a function f of x, and derivative of that function at that point x0 exists, then the derivative has to be 0. Okay? So let's investigate these things a little bit more. Obviously, we already said, well, if we had a function maximum minimum, we have to have derivative equals to 0. And obviously, to have derivative equals to 0, we have to assume the derivative exists. But is it possible for a function not to have derivative? Okay? And the answer is yes. There are functions that don't have well-known functions that don't have derivatives. For example, absolute value of x. What happened with this function? It has behaved like f of x equals x on the right, and derivative on the right is 1. On the left, it behaves as minus x, and derivative is equal to minus 1. So essentially, derivative jumps when it goes through this point, and that's the point where derivative does not exist. And also, when you look at the graph of a function, you normally can point out the points where derivatives don't exist. Those are the points where you normally have those sharp, points, okay, sharpies. That's an indication there's no derivative. So let's investigate what's going on around this point, okay? And what's going on here is that the function has to be, to have a derivative, this limit has to exist for both delta x positive and delta x negative. And that limit has to coincide on both sides. Otherwise, we'll say, well, there's no derivative, okay? If a limit on the left and limit on the right do not coincide. So let's see what's happening. First case, let's take delta x greater than 0. We say it's going to 0, but it's going to be always positive. So derivative at point 0, we say 0 plus means from the positive side, would be f of delta x minus f of 0 divided by delta x. Well, f of x here is x, so f of delta x is just delta x, and f of 0 is 0. So we get delta x over delta x, we get 1. Now, if I look at the negative values of delta x, again, we just keep delta x negative and shrink it to 0. In this case, we have derivative from the left, and the function f of x here is minus x. So f of delta x will be minus delta x. So minus delta x divided by delta x, we get minus 1. So if I look at this derivative from the left and from the right, I'm going to get different answers. It means there is no derivative. Okay? We cannot reconcile those two values. But we can actually come up with a more clever approach. So what we can do, we can shrink delta x going to 0, but we can switch the location. We can first move on the right, then switch to the left, then switch to the right, switch to the left, and so on, and do it infinite number of times. And every time when we switch, we're going to get a limit as 1, then minus 1, 1, minus 1, 1, minus 1, and so. And we will never converge. We will actually never going to have a unique answer when we take that limit. So that limit is completely, does not exist, okay? At least, limits on the sides, right-sided limit and left-sided limit have specific values. But what I was talking about, like flipping the side, that wouldn't have any limit. But it's allowable thing to do actually, as long as delta x goes to 0. And graphically, what does it mean? Well, the derivative is the slope of a tangent line. Well, where's the tangent line here? Well, I can draw it like this. In this case, derivative is 0, but I can draw it like this. Positive derivative. Draw it like this. It's negative. Which one is the correct one? Well, who knows? And that's why they're all good. That's why there's no limit. There's no derivative. All right? So, and now we kind of should understand how to find maxima and minima of this function. Okay? So, if you have something crazy like this, what we're going to do, you're going to find derivatives of this function, find the points where derivative is 0 or does not exist. So here are the points. You have these points, which give you maximum, zero derivative. You have these points with zero slope, zero derivative, that are minima. You have point like this, the green one, that has zero derivative, but there's no maximum minima. And you also have those purple points, which indicate no derivative. They're sharp turns. And now what we're going to do, we're going to look at the signs of the derivative to the left and to the right of all these points. I start with very left. The function is increasing here. Derivative is positive. Then function is decreasing past the maximum. Derivative is negative. Then derivative is positive. Then derivative is negative. Then derivative positive, negative, right here. Then negative again, positive, negative, positive, negative, positive, negative. If on one side of my point where derivative is zero or does not exist, on the left the function is positive and on the right the function is negative, it means I have a maximum. If I have the opposite, I have a minimum. Okay? And notice it works both for the cases where derivative exists, and zero, and for the case when derivative doesn't exist, like here. We're going up, positive derivative, we're going down, negative derivative, I have a maximum here. But here's the case when derivative doesn't change. It was negative, negative, and we keep decreasing, okay? No maxima or minimum, okay? Let's look at a couple of examples. Consider this function, 2x cubed minus 3x squared minus 12x plus 12. It's a cubic polynomial. First we do is calculate the derivative of it. It's a quadratic function like this. The next thing we need to do, we need to find where this derivative is zero and where it doesn't exist. Well, quadratic polynomial exists everywhere from minus to plus infinity, but it does have zeros. So if we solve this equation, this quadratic equation, we find there are two zeros. It's x equals to minus 1 and x equals to 2. Now, knowing this information, we can rewrite the derivative. We can actually factor it and get expression like this. And this expression is very convenient for us to study the behavior of this derivative, to see where this derivative is positive and where it's negative. So we get our number line, we put our zeros as minus 1 and 2, and now what we need to do is to see what kind of derivative, what sign of the derivative we have for x less than minus 1, between minus 1 and 2, and greater than 2. Okay? To do that, really what you need to do is to pick up x in 1x in the range of x less than minus 1, 1x between minus 1 and 2, and 1x above 2. Okay? And what we find that the sign of that x will correspond to sign of all x's in that particular range. Okay? So for example, we're interested in the sign of the derivative for x less than minus 1. Take a value here, say x equals to minus 2, and plug in this formula and see what the sign of f prime x is at the point of minus 2. So what do we get? We get minus 2 plus 1. We get minus 1 here, negative number. And here minus 2 is minus 4. So both parentheses give us negative numbers. So when we multiply two negative numbers, we get a positive number. So at point of x equals to minus 2, derivative is positive, but that means derivative is going to be positive for any x below minus 1. So this is positive. Now we want to know the derivative, sign of the derivative for x between minus 1 and 2. Well, pick up any point between minus 1 and 2. Let's pick up 0. Well, plug 0 into the formula for the derivative. We get 6 times 1 times minus 2. That's a negative number. So the derivative in whole range is going to be negative. Now we're interested in derivative above 2. Well, okay, pick up a number, let's say 3. What do we get? 6 times 3 plus 1, 4, times 3 minus 2, 1. It's a positive number. So derivative in this range is also positive, like in the beginning. So now we can kind of figure out how the function behaves. It's easy. Positive derivative function goes up, negative derivative function goes down. So first function goes up, and down, then up again. Okay? So what does it mean? It means that point of minus 1 is a point of maximum, and point of 2 is a point of minimum. And this is how this function is going to look like. Okay? The top point is maximum, bottom point is minimum. We can calculate the coordinates of these 2 points. We know x, we can find y. One point has coordinate minus 1, 19. The other has 2, minus 8. So obviously, if you look at the vertical coordinate, the maximum has a vertical positive coordinate, minimum has negative. It means that 0, y is going to be achieved somewhere in between of these 2 points. And it also tells us that this particular polynomial has 3 real roots. Okay? So derivative investigation of the derivative could actually help us to figure out how many different roots the polynomials can have, or any function can have. In this particular case, we know it's 3. Okay? Let's consider another function, 4x cubed minus x to the 4th. Again, take derivative. Notice there's a factor 4x squared that both of these terms have. We can pull it out, and this way we can easily factorize this derivative, right? We can quickly see that f prime is 0 when x equals to 0 or 3. And f prime is defined from minus to plus infinity, so there is no points where derivative does not exist. So again, these are our roots for the derivative. We get our line, number line, this point is 0 and 3 zeros. And what we want to do, we want to check on the sign of the derivative in all these 3 intervals. Okay? Below 0, just pick up any number if you want. Pick up, say, minus 1. You get 4 times minus 1 squared, which is 1, times 3 minus minus 1, which is 4. So derivative is positive. Between 0 and 3, again, pick up any point. Let's say we pick up point 1. We find that x squared is positive, and 3 minus 1 is also positive, so we get positive here again. And for x greater than 3, we find that the x squared is still positive, but the second parenthesis is negative. Okay? So what do we have here? We're going up, we're going up, we're going down. Okay? So it tells you that point 0 is neither maximum nor minimum. We just go through this point and keep going up. But point 3 is actually the point where we're going up first and down is a maximum. This is how our function is going to look like. This is our point no minimum maximum. This is our point of maximum. These are the coordinates, and we can also draw a horizontal axis, and we can easily see that this particular polynomial will have 2 roots. Although it's a 4th order polynomial, only 2 roots here. Okay? And the last example is x minus 1 to the power 2 third minus 3. Now there's no problem with x minus 1 to be put in the power like 1/3, and that's because cubic root doesn't care. It can handle both positive and negative numbers. Okay. So the function is defined everywhere. But next thing we want to do is calculate the derivative. The derivative looks like this. Next thing is, well, we need to find the zeros of the derivative and points where the derivatives don't exist. Now, if you look at this, derivative equals to 0, 1 numerator of this function equals to 0. Well, it's equal to 2 as far as I can see. It's now a 0, so there's no zeros of this function. But there's a point where denominator goes to 0, and that's the point x equals to 1. So that's the point where derivative does not exist. So what we do, we draw our number line and we put that point x equal to 1 where derivative doesn't exist. And the next thing we need to do is to figure out what's the derivative to the left of this point and what the derivative to the right of this point. I mean, the sign of the derivatives to the left and to the right. Well, to see what's going on to the left, we can pick up any value you want, say x equals to 0, with x square root, cubic root of minus 1, which is minus 1. So derivative is negative here. And if we go above 1, we can pick up, say, 2. X equals to 2, we get a cubic root of 1, which is 1. So here the derivative is positive. So on the second part, above 1 function goes up, below 1 function goes down. So you notice at point 1 we have minimum. And this is how our function is going to look like. So notice the sharpness of that point where derivative doesn't exist. That sharpness normally indicates that there's no derivative. All right?